Okay, today it's the higher symmetries of cyclic type, and I will be doing a good deal of the study of wave dynamics and results from looking at these solutions. But first we have to get the solutions, which means a spectral resolution. I'll pick the hexagonal symmetry today, at least to start, and then we'll show how that generalizes. We were just looking at, in the last lecture, at threefold. We're going for six mostly today. But I want to show some of the physics of the parameters and the Fourier analysis, because that's really what this is. This is a sophisticated Fourier analysis using the cyclic group representations. And I'd like to show how it lets you do some interesting physics, the gauge physics of an oscillating wave system. And then we'll take on a little bit more about the wave dynamics that results and how to use the dispersion functions, what they really mean and what you can do with them. And we'll introduce some of the things in connection with that, the expo cosine identity we've already seen, but not for an entire wave. And the remainder of the lecture will be devoted to the space-time, that is the dynamics that most people are used to, and the inverse space-time, that's frequency wave number, views of a wave, and how you can make wave coordinates in either of these two. And then look at the difference between wave packets and pulses, which are going to be the main topic of the lecture 13, which follows this one, and the continuous waves, the comparison of those two extremes of Fourier analysis, basically. And we'll come back to linear dispersion. I'll look at the Bohr-Schrödinger dispersion, and then I'll show you how actually to eventually derive matter wave dispersion, which is what that is. How to make space-time coordinates using lasers is, I think, the high point at the end of this lecture. So let's go ahead here and look first at the spectral resolution of something that has symmetry C6, a hexagonal cyclic group. And as you can see, the group has elements starting with, if you read the column, an element R. That will be a rotation by just 60 degrees, half the angle that we had in C3. Then R squared will be a 120-degree rotation, and so on. A 180-degree rotation, a flip, is something we didn't have in the group. We talked about C3, the subgroup of this. I've indicated that by a green color. There's something special about flipping something through 180 degrees. Then the inverse of the R squared is R to the fourth, and the inverse of R itself is R to the fifth. So we're doing the arithmetic modulo 6 when we number things with the two kinds of quantum numbers that we talked about. The first of them being the exponent or power that designates one of 6 points on a hexagon. Now this is what I call the GG dagger form of a group table that I mentioned for C3. And basically, after I've put down an order, an acceptable ordering of the elements, very easy to do for this group because it's just powers, I then put the inverses, that is the dagger, if this is unitary operators, up here. So that every time I multiply something by its inverse, I get a 1 on the diagonal of the group multiplication table. So that means that I'm setting this up so that I can read the regular representation, all 6 matrices that obey this group table for the elements, 5 elements besides the identity. And of course the identity matrix, we know that has to be 1s on the diagonal, so that's why basically I'm doing this little trick here to get the group table set up. So the representation of the element r to the first power, which is this one, is just gotten by putting a 1 in each of the places. You see there's a bunch of things that going back to that 5 1s here, and then the 6th one is this r that's up in the corner. Okay? So each of these matrices has been generated by looking at this table. And here's the 180-degree rotation operator. And each of them has a parameter, a number, with different colors on it. No particular significance to those colors, except that when I look at the Hamiltonian here, you can see our number 1 red very clearly displayed. So this is the actual Hamiltonian matrix using now 1, 2, 3, 4, 5, 6 parameters. It might be more than that because all of these parameters, with the possible exception of this one and this one, the red and the green, could be complex. So we'll get into that later on. In any case, this is the idea is that the C6 multiplication table gives us all of the matrices that make up a most general Hamiltonian matrix for this symmetry. And the name for these, as I said before, is a very common name that you'll find in almost every textbook, the regular representation of the group. Okay, now, as I've said, we're making this by putting a 1 wherever an element appears, in this case the R3 element. Now that is the one matrix you see that's, all of these are supposed to be unitary matrices, but this one is both unitary and Hermitian. That is, it's more than Hermitian, it's real Hermitian, which means it's a symmetric matrix. Okay? The only other symmetric matrix here is the trivial case, which is the unit operator. Okay, so this is the basic mathematics of this thing, and this is what I'm really thinking of. We're getting a group table giving us all the C6 allowed Hamiltonians, and each of those parameters determines a tunneling path, if this were a quantum Hamiltonian, or some kind of spring or coupling connection if it's a classical problem. The easiest one, and this is what we'll call the block model for a lattice, and this is a very simple lattice, hexagonal lattice, consists of just the R1 and the R5. That is R1 and R minus 1. Minus 1 is 5 modulo 6, or vice versa. 5 minus 1 is 5 modulo 6. So we have here an operator that would take us from what will be called our original state. This time our original state will be on top. That's r to the 0 power, okay? And there is a self-energy, you might say, for that one. So you might draw a little line, a little black line indicating this parameter is a little circle on the original state. And then moving at 60 degrees, and this we're taking positive clockwise, like our phasors. That is this state right here. So this would be the state that we would designate by r to the first power. So we're going to be counting 1, 2, 3, 4, 5. And right now we're only giving matrix elements for the connection of 0 to 1 and minus 1, which is 5 modulo 6. Okay, so that's most of the solid state physics books start out with Hamiltonians that are cousins to this thing. And it's called the block Hamiltonian. Nearest neighbor coupling only. But what this is showing us is that there are a lot of other possible couplings, a different coupling in a sense for each of these parameters. And furthermore, many of the parameters can be complex, including these two that we started with. So the entire Hamiltonian will be something like that. That's the most general Hamiltonian with all of the neighbors coupled to all of the others, and having C6 symmetry. Okay? So this is the same thing we did with the 3, but it's getting a little more complicated. Okay, now this is just a picture of a Hamiltonian that would be the block model. It would consist of a parameter on the diagonal, H1, and then an R and an R bar, just trying to find notation that isn't in indices like this one. And very often we choose the sign for things that would fit a mechanical device like that. Or, as it turns out, if this were quantum mechanical tunneling, there is almost always a negative sign. It's very hard to not have that be negative. So there's the first neighbor choice right there. Now another possibility is, well, before I say that, I should point out that if you have conjugation symmetry, then first of all, the diagonal coefficient here has to be real. Okay, so that is just a real number for sure. And then the question is what to do about the R5 and the R1. Well, R1 has got to be the complex conjugation of R5. Okay? But R1 itself does not have to be real. If it is real, then it's equal to R5. But if it's not, then both R1 and R5 have what we call a gauge term, and we'll get to that at the end of this block discussion here. So right now, I say the elementary block model just assumes they're both real, so, and negative. So there is the Hamiltonian that most people would think of if they were thinking of a coupled hexagon. Okay, and that would be the end of the story. But if you were to say, oh, I'm not even going to have nearest neighbor, I'm going to have next nearest neighbor. Well, then by doing that, in this case, you break the thing into two problems like we had in the last lecture that involve a triple symmetry. So these are two triple symmetries, sort of a Star of David, sitting there, uncoupled from each other, but coupled across the next nearest neighbor. Okay, so there we are. And in this case, it's a little bit confusing here because I've turned it over. The point 0 is now at the bottom like it was for the thing we did last time. And we're doing this counterclockwise numbering here. But whatever, the Hamiltonian that's written this way would be gotten in either case of labeling.
Bill, Professor Harter?
Yes.
Could I posit one thing and then we just shoot it down if it's wrong?
Yeah.
You just mentioned that for the case where we have only the second neighbor coupling,
right,
it turns into a 2C3 problem. So if we alternated our bases and rewrote the Hamiltonian, it would be block diagonal.
That's correct.
3 by 3.
We're gonna see something like that happening. Absolutely. Once you saw this, you say, hey, I've got two systems here, let's do this one, and then just copy it. But that'll happen automatically when we do this, as we see, because we're going all the way to get diagonal here, and we'll not stop at the block, so to speak. Okay, now, here, this one has a conjugation symmetry as well. The next second nearest neighbor couplings are R4 and R2. And you see R4 here has to be the conjugate of R2s right there, and vice versa. The R2s have to be conjugate to the R4s that are down here. And if that's the case, if we assume both are real, then R2 equals R4 conjugate, and if they're real, they're equal to a single real number, which again, we're going to put a minus sign on that. And by the way, we did have a minus sign on that for the C3 problem we did before. However, this one is 3 diatomics, okay, with essentially 2 T springs between there. Now, in this case, T has to be real. This R3 here, R3 star has to be equal to R3, because that's what would actually be sitting there. There'd be R3 right opposite R3 on this side. So if I demand that they be Hermitian, I can't have them be complex. So this would just be a T. I'm putting the minus on because it's the same kind of coupling that requires that physically. All right, so that's the situation for this.
What do we have T real?
Say again.
What do we have T real?
Do we?
T. Why do T real? What to? Why?
There's a word there that I'm not picking up.
Sorry. Why T's are real?
Oh, why is this constant? That's.
Yeah.
Let's just go back to the original matrix. Why does this R3 here have to be real? That's what you're asking, right? Okay. Well, first of all, these R3s here are exactly the same as these R3s down here, right? There is only one parameter to describe the 180 cross-town coupling.
They are the same, exactly.
And if they're going to sit in the matrix like that, then every number in here has to be the conjugate of its partner across the way here.
It is R4.
Yeah, here R2 hits R4, right? So it can be complex. But you come up to this one,
it's impossible.
It's impossible. That's a subtle point. And thank you for the question. That we're going to have special little bands that have to be real in matrices like this. We're going to think of matrices are huge for this type of system and systems that come later. Now, time to diagonalize. That means time to spectrally resolve these operators. And this can be done just like the C3 case all at once. Every one of these operators, x equal r to some power, must satisfy x to the 6th equal 1. These are all operators that will take you back home again if you do them 6 times. Some of them will take you back at 3 steps. For example, r squared would do that. But all of them will take you back if you do as many as 6. So what we're looking for are the roots of unity, that is the 6th roots of 1, okay, for eigenvalues. And we're going to use a notation we set up last time that's very standard for representation of a group element, r to any power, okay, starting with r to the 1st power, which will be given by e to the 2 pi I m over 6. And then if I consider a higher power than 1 of this, okay, I will get m times p over 6 with the 2 pi I factor. All right? So these are the numbers. These are the characters. There's the chi that represents a character with a superscript that corresponds to the integer in the exponent that we call momentum. So the momentum is quantized. That's just counting wave nodes, basically, or pairs of nodes. There are going to be 6 pairs of nodes for m equals 6 and so forth. Then what I'm talking about in the denominator here is the coordinate of where you are. What point are you located at? What point P, or what power, when I'm talking about the group operator that defines where you are. So in general, we're going to be looking at a character that has momentum, irreducible representation label, always be a subscript. That's going to work for all of the stuff we do in this course. And then the thing that's this sub here is telling you, well, which element is being represented, which R to the P is being represented. Okay, so this is like a coordinate. Where are you on the lattice? What point are you on the lattice? Okay, and the other notation is the wave function notation. Psi, which is the conjugate of the chi. So we're sticking to that convention come hell or high water. I mean, we have to do that. Simply, there's enough notational headaches in group theory. We're trying to keep them to a minimum. And I'm listing here all of the different momentum states for the point number 1. In other words, what's the phase at point number 1, okay? And there are a couple of little modular arithmetic things here, but basically we're going through all the powers of 2 pi I to the 6th. And the third power just comes out to be -1. E to the pi I is equal to -1. Okay, so those are the numbers we're using. And the idea of all of this is, this whole course, is that symmetry groups or algebras, we often are working with things that aren't necessarily groups, and it will be convenient to do that. In fact, group theory really shouldn't exist at all. We should just go straight to the algebra of groups if we're going to do physics. Don't stop at go. So anyway, these algebras know their roots, and we'll tell them to you if you ask nicely. Okay, so what we're getting by this knowledge is to efficiently find invariant projectors, the irreducible projectors, irreducible representations. I'm going to be using that little name IRREFs. That's a mouthful. And finally, the Hamiltonian eigenvalues, eigenvectors, transition matrices. We will not talk about that today, but we will talk about how the eigenvalues make dispersion functions that are very useful for all kinds of physics. Okay. So once again, here are the 6 roots of unity, 1 and -1. And then e to the 2 pi I over 6, e to the -2 pi I over 6, which we call e to the 5th power. Then e to the 2 times 2 pi I over 6. Okay, and then finally 3 times 2 pi over 6, which is -1. Okay, so 6 roots of 1. That's the key. Now we need a better picture of the roots and all of the characters. That is coming. But before we go there, we need to express every one of the elements, you see, each of them for all powers, 0 through 5, or 1 through 6. I have to express all of them as a expansion, a spectral expansion in idempotence. Okay? So I'm just doing this in a very direct way. I'm saying, okay, I'm just going to line up a matrix here with all these eigenvalues. And then each one of these things is what a projector will look like if you're in its eigenbasis. And here's the multiplication table for all of the 6 projectors. We know what that is. It has to be an idempotent. Furthermore, they have to be Hermitian. So I'm kind of stuck with just having a multiplication table in which each of these squares up to itself. P3 squared squares up to itself, P3, and so forth. All of those projectors that are sitting here square up to themselves. Well, that's what this matrix and this matrix and this matrix, they all do that, you see. So this is just sort of telling the obvious about this expansion. Okay? And we know what the eigenvalues are for each of these things. There they are. Okay? So this is treating the projectors to start with as eigenvalue placeholders. And of course they have the idempotent products and the orthonormality as well. If I multiply this matrix by this matrix or any of the others, it's 0 for sure, because there's nothing waiting over here for that one when I do the product, and that one's not going to get anything either. So there's your orthonormality. Okay? So this is really just stating the obvious. And of course, most important are the eigenequations. That is, that the group operator times a projector should be giving you a character, eigenvalue, that goes with that particular projector. It really needs to, well, there it is. The end is sort of pushed over a bit there. So these characters, 0 through 3, 4, 5, and finally 6 is the same as that, are the cyclic eigenvalues. So, doing the inverse of this, okay, is to simply replace these guys with the star of them. The star is the psi, okay? So, when we make a character table, and that's what's being done here, I'm simply listing each of these psi's for powers, positions, p equals 0, 1 through 5, okay? And I'm doing one with a 0th power momentum, and then I'm doing one with m equal to 1, m equal to 2, 3, 4, and 5. So there's a very silly way to write a character table, but it shows you who's going where. And then there's the actual characters, the actual roots of unity written as phasors. It may be a little hard on the camera to see. The little white arrow that lives in this thing, but that's one of the things that we now have for you to draw for any n, including up to 1,000 even if you want to try, a character table for C big N. This is just 6 here. So we've got a momentum here of 0 mod 6, 1 mod 6, and 2 mod 6, and then 3 mod 6. You see, it has just simply a real number, 1, which is here and here. That's at the clock at 12 o'clock, so to speak. And then minus 1. Minus 1 is the opposite color to red, so that's kind of the way we label phases by colors in a sort of a rainbow spectral order. So this one is 1, minus 1, 1, minus 1, 1, minus 1. And this particular value of momentum, 3, is called the Brillouin band boundary, but we'll get into notation of that later on. In any case, I think you should look at this table a little bit here and notice that if I were to just draw the waves, the real and the imaginary parts, I believe that's real and that's imaginary. It's supposed to be a little more gray, the imaginary part leading by 90 degrees there. You see that as I go down here, I have one whole wave. Here I have no wave. It's just a straight line oscillating what a frequency 0 does. And then I have one wave here. That's momentum 1. That's what quantum number really means. I've got one wave. And then 2, I've got 2 waves, you see, before I start over again. And then 3 waves here. 1, 2, 3. You see, complete wavelengths, and I start over again. And then 4 waves. And then finally 5 waves. But if you actually plot the position of the phasor, without drawing the whole phasor at each point, then you'll notice that this wave right here looks very much, in fact, is the same as this wave right here. In other words, modulo 6, these things are just 1 and minus 1. And then, same thing for 2. You see, 2 waves, right? Well, down here we have 4 waves, but look at the dots, you see. They're just going to be in the same position as the number 2 wave, this right here. So compare this wave with this wave, and they're the same. It's just that one of them's going this way, and the other one's going that way. Okay? That's the thing that doesn't show until you look at the imaginary part. Okay? So I thought you ought to see that. And then this one can't decide. This is a standing wave. It isn't going, it's going both directions and no direction, like this one. Okay, so this is now getting to a sufficient complexity to begin talking about continuous waves. But it's a finite symmetry, so to that extent, it can't be quite continuous. It's just starting to get that way. Well, no matter what we set the resolution to, it's pretty clear where we stand here. There's the one wave, okay, with its pieces showing very nicely. There's 2 waves with the settings in there. And if we were talking about something that was C3, we've already seen this guy, right? That's this, subgroup symmetry showing that. And then this one is alternating. That's a real standing wave. And then here's this guy. Well, he's very much like this one. You see the colors, by looking at the colors, you can see they're very much related. This is the conjugate of that one. Complex conjugate of that one. And then this one, the same as that one. Purple's here, purple's there, right? This one is headed, actually, this way. I'm sorry, this one's headed that way, this one's headed this way. Using the notation that I find fit the most group theory works in the literature. Character equal e to the minus I m p 2 pi over our symmetry number 6. And they say wave function conjugate to the psi. Okay, so the psi doesn't have a minus sign. Psi is e to the I k x. Well, k sub momentum r position at p point. Okay, so this is the formula for all of these complex numbers here, and if you replace this by n, it's the formula for all the cyclic groups of order n. I mean, it's one group for each n. Okay? Remember the lattice position vector Rp is equal to some lattice spacing times the integer p. And then the wave vector, 2 pi over lambda, okay? That's this thing right here, 2 pi m over 6 times L. Flip it over, wavelength is 2 pi over k. That's the total circumference of the cyclic circle divided by the momentum. And that just is saying that the wavelength has to be an integer fraction of the entire circumference. First quantization. Okay? So everything is obeying rules that we would have learned if we just studied the Bohr quantization of a wave on a ring. We're just doing a very sophisticated Fourier analysis of it. So we do have a little bit of a problem is the phases that we actually put in a character table rotate backwards. They're conjugate waves. That's just the way the literature is. I could have said, I'm not going to do it that way. I'm going to make them behave the way they should. But this is a situation where it's probably better to match the literature. So this is what you see if you look up in a library. And the idea is that epsilon is 2 pi I to the 6th, and there are the various values of it, where they usually will write a -1 if it's e to the pi I. Okay? In the library, though, you will not find, except in my books yet, a picture like that. So don't expect for a long time. Someday, that's the way we'll do it. But not yet. Okay? This is the old program making character tables up to 6. There's a C5. You'll notice it doesn't have a Brillouin zone down here anywhere. It's because it's odd. But C4 does. Half of 4 is integer. Okay? And C6 does. Okay? So we'll talk a little bit about what all that means. Here is C7. It does not have, and none of the odd cyclic groups will have, a real wave anywhere except at 0. But halfway for every other wave that's even, C8, stop at 4, there's the Brillouin zone. We'll see what that means as we go through and study the wave dynamics a little bit. But these are all things that you can get on the program WaveIt. They were all made by WaveIt, and they're certainly a lot better than the old WaveIt, which is, you know, it was fun for a while, but we're past that, at least as far as this goes. We're slowly crawling out into the world. 7 is quite pretty. And again, we're coloring these things, you know, in a spectral order. When you start getting large values, okay, this is 24, okay, you get a picture here, okay, there's the thing that you start with, a wave that has no kinks, and then you have 1 kink, then you have 2, you see, and then you have 3, and so forth, okay? Go back to 1 and look at the very last one down there. 23, that's 1 less than 24. Same color. It's a rainbow, nice smooth rainbow from red to red, essentially. Okay, around the color wheel. Okay? And if you look at the settings of the phasors, you really can't tell much difference between those at the very bottom and the ones that are next to the top, right there. So that's a nice big example of everything that we're talking about. 24, okay? A 24-hour clock, a European clock, right? It's got 24 numbers on it, right? Want to go for 72? This is all, you can do this on WaveIt very nice, very quickly. Just put in a number, see what happens. Okay? And here, I've not bothered to draw the arrows because it degrades the color. Now we're getting to the pixel level, you see. Okay? Now, you'll notice hyperbola sort of in there, right? This thing is a product of M and P, right? The phase is determined by a product of momentum and power, or point, right? This is momentum, that's power. This is what a Fourier transform looks like. When you're doing an integral Fourier transform, you're doing it with n equals 72 million, or some huge number, right? A continuum. This is the matrix. This is what it looks like. And when MP is a constant, you have the same color roughly. But then the numbers start playing with each other, the integers. There's all sorts of number theory, depending on whether I make this odd or even or divisible by 5 or divisible by, various numbers that are important.
Prime?
You could, yeah, if you make it prime, it's not as pretty as this. This one breaks up into little subsections and sub-villages, you see. Now we're going to see that in the dynamics in the next lecture, which we call revivals and all kinds of funny names given to beats of beats of beats of beats. But that's what we're going to be dealing with. And all of this stuff is going to come alive in the dynamics. Now, in the Unit 3, Chapter 8 through Chapter 9 of the Quantum Theory for Computer Age, you will find that I introduce quantum mechanics dynamics using not a polarized X and Y, but a thing that can polarize into 6 states, a U6 analyzer. Okay, so you might be aware of that. And the idea is that the beam will split into 6 things, and then they'll all couple with each other using coefficients like we're talking about, and bring you a new state.
Sweet.
So it's the whole idea of splitting and then recombining. That's a analyzer operator. And then there'll be measurement analyzer counters as well, just like we had with polarization. So this is a good way, I think, to think about the beginnings of quantum mechanics in any case. Now what I'd like to do is talk about the complete sets of coupling parameters and dispersion. So this is just sort of a nice, precise and concise expression of what we've just done here. We've said, okay, Hamiltonian is a linear combination of these group operators to some power. And this is going to be summed from 0 to n minus 1. So this is C6 with n equal to 6. I would be summing to 5, 0 through 5. With those parameters 0 through 5 and the powers 0 through 5 of the fundamentals, in this case, 60-degree rotation. So what I'm going to do is I'm going to break the RP into its spectral decomposition. So there's RP written out as a linear combination of the projectors. And the linear combination coefficients are the characters. The better name for later on would be D, M, and then a matrix, not just a single number, representing the operator. We'll get to that. Right now it's a number, so I'm using the character notation, which is appropriate. But the idea is that I can combine all of this into an eigenvalue. The eigenvalue is simply the sum of those parameters now over the points, okay? And that is a function of those points, and it's also a function of the momentum. That's your dispersion function. So we're going to look at those. But you can see, kind of in one line, we do this whole group theoretical driven Fourier analysis. In any case, here's an example. If I only turn on the parameters r sub 1 and r sub 5 and make them both equal to minus r. So here's r sub 1, here's r sub 5, that's minus 1 modulo 6, okay? And I know that these things are e to the 2 pi I m over 6, okay? And I'm summing them with both being equal, r1 equal to r minus 1 equal to this r. Then I get a cosine with a factor of 2, exponential e to the IA plus e to the I minus a is what I'm getting from this one. That's cosine of a times 2. All right, so that's the dispersion function of m, right there. That's this thing. And that's all there is to it. That's the block dispersion function. Elementary block model. Okay? All right. All right. How do you plot this? I think the most convenient way to plot this is to simply draw a hexagon like this, okay? And then at equal spaces, lay it out. There's the cosine right here. So the ground state is right here. One of the first excited states, the plus one, is right there. There's the minus one over there. So the two sides of the band K axis, and this is the frequency axis right here. This is per space time. This is inverse time. This is inverse space. Okay? So we're plotting here the eigenvalues as a function of the m value. Okay, m equals 0, 1, 2, 3. That's the Brillouin zone. Okay, minus 3. We're not going to count that twice. We'll just count 1 for that. And that's because my two real waves are the bottom and the top. In between, they're complex. The eigenstates are complex. There are these functions here, which are complex for everything except m equals 0, m equals 3. Okay, m equals 0, m equals 3. But the actual energy that you have is this thing. Okay? Here we're plotting it with H1 being 2r, so that I get a 0 right here at the start, and then I come up. Okay. All right. Well, that means that this spectrum, like the one that we had with the three-bodied object, has a double degeneracy here, and then another one, and then a single at the Brillouin zone. We didn't have a Brillouin zone for the odd one that we did last time. I'll lecture. C3 odd, no Brillouin zone. C6 even, yes. I've got half of 6 up there. It is an important state that is alternating. It's got the most wave number that you can have with 6 things. And not be just that thing right there. We'll look at that later. Okay, suppose I had second neighbor coupling, just for the sake of argument. All right? Well, it'd be the same kind of a thing, only it would involve these s's, and it would be 2 pi, 2 times 2 pi, 4 pi m over 6. So what I get is a cosine wave that comes to the top quicker, twice as fast, or at half of this one's distance, and then goes back down again and does the same thing on the other side. It's a triangle, equilateral triangle, flipped over, just like it was for the 3 thing, except now there's 2 of them. There's a 0,6 and a 3,6. Okay, 3,6 has been brought down. Momentum 3 is now 0 energy along with momentum 0. And then there are these 2 guys, plus and minus 2 mod 6 and plus and minus 1 mod 6 are both degenerate. That is, they're pairs by themselves, but the 2 pairs have the same energy. So it's a quadruple, a quartet located there, 2 doublets. And here we have 2 singlets. Okay, so that's a dispersion function for this system. And finally, with third neighbor couplings, I'm just going to have 2 of our C2 problems on top of each other. You see, 3 of our C2 problems on top of each other. Okay? So I'll have symmetric and isometric, symmetric and isometric, and then I've got another one over here, symmetric, anti-symmetric. So I'm going to have a triple degenerate, a triplet here, and then I'm going to have a triplet. So I'll have a ground triplet and an excited triplet. Okay? That's the way it should be. This is three separate C2 problems, like our couple pendulum system. Okay? Now, of course, the thing that we're really interested in for the general case is a linear combination of all of these. And that is where this business of Fourier analysis really comes in. So what I'm doing here is I'm just rewriting the eigenvalue expression, okay, that we have just been talking about, and then this RP here, using our momentum states, which have that wave function, I'm getting something that looks, well, it is that, but I can write it this way. This is a general expression. Now we have a general relationship here in terms of Fourier series, complete with the possibility that it's a complex number. If I don't have a gauge angle here, then this is going to reduce. But if it does, we'll discuss that later. But I'm going to set the gauge phase to 0 now, so that I end up with a block eigenvalues, a Fourier series with 4 Fourier parameters. Okay? Starting with the obvious one that sets the origin of the band. And then an R1, which is equal to R minus 1, we'll call that R. An R2 that's equal to R minus 2 has to be, if it's going to be real, a real little s here. And finally this one, always real, the t. So I'm ending up here with 1, 2, 3, 4 real parameters. Okay? And that's the way it looks. So here's a dispersion function being written out as a sum of cosines. And this one's really easy. It's just up, down, depending on whether you're odd or even. But these two guys here are those two cosines. This is the block cosine that just goes like that. And this is the one that does it twice. Right here. And this is the one that does it 3 times, but that ends up being odd and even. Okay? So that gives us these levels, and they're degenerates, you see. So in M4 numbers, I have 4 parameters. And this is what's cool about group theory, is it's going to organize stuff for you. When there's degeneracies, it's not going to waste parameters on the things that have the same energy. And so we have 4 parameters. That means we're going to have 4 eigenvalues. Okay? And they're going to be invertible. In other words, I can decide what energies I want to have and make a designer oscillator, you see, by solving this equation to give me the parameters I need to make that oscillator have eigenvalues wherever I want them to be. I can pick these 4 numbers. Now that's where this starts to get powerful. But that's just Fourier analysis, you see. But the group theory leads you into the Fourier analysis to let you pull this kind of stunt. Okay? Running the problem backwards and forwards. That's really what you can call this. All right? Now the general block eigenvalues have 6 Fourier parameters with non-zero gauges. Okay? Stick those numbers into those cosines there. Okay, and that one doesn't get to play the game because it has to be real. But these guys can play. So you got 2 more parameters. Now you've got 6 parameters. 6 real parameters. To give you 6 real eigenvalues for the Hermitian operator. Hermitian operators have to have real eigenvalues. Okay, and this, if it's a unitary operator, well, no, then we have more parameters. But for the Hamiltonian, this is the end of the road. Now that's discussing unitary operators, a whole other thing. It's discussing scattering on one of these C6 things like I have in the textbook. That's really cool. We have not really explored that very much, but I think it should be done. If you're going to play information science, at least you should know how to do that. So we're going to have 6 levels in general. Okay? And I'll leave that as an exercise to figure out how you would do designer with 6 parameters where you don't have any degeneracies at all. That's the ultimate C6 symmetry. Okay? I want to show instead the geometrical solution, geometrical way to view it. Okay? Go back to our 3rd step, okay, where we wrote the dispersion function. Okay? And let's just do it complex for only the nearest neighbor. The nearest neighbor couplings. Only thing I'm going to try. We're going to make them complex. Okay, so I'm going to have an extra parameter here. I'm going to have the parameters I already had, which was 2, and then I'm going to have an addition to that, this gauge thing I'm going to stick in and allow it to move. Okay, so nearest neighbor coupling for Hermitian matrix, the complex components are conjugates of each other. So R minus 1 has to be this thing if R1 is this thing. But that's an extra parameter, that phi there, the gauge, okay? Now where would you encounter this? The simplest way that I can imagine encountering this is to simply put this thing on a rotating turntable and watch it with one of our U2 periscopes, okay? Watch how it vibrates. The idea is that if you're rotating this way, the wave is going to have an extra speed going this way that it doesn't have going the other way. You see. Now you know this probably better, unless you've been playing with Coriolis molecules. You probably know that if I have a bunch of charges on a thing like this and I put a magnetic field in there, that's equivalent to rotation in a chiral sort of way. Okay? And so you're going to see Zeeman splitting of the M levels. The M plus and minus are going to split. That's first order Zeeman effect that we're talking about, you see. So you don't have to use this word gauge, this fancy word gauge. That goes back to the earliest spectroscopy, the spectroscopy that was done first looking at the sun. And the anomalous Zeeman effect is what they saw. They were very confused by it. It took a long time to sort that out. But this is the eigenvalue situation where I put in that extra phase. So it doesn't change the answer much. It simply gives me an extra phase shift of the cosine. And what does that do? When you put a chirality, a C-type Hamiltonian to this thing and make it, you know, distinguish between right and left, you're going to split the doublets for sure. But how do they split? What's the way to do it? Well, according to this, you simply take the hexagon that you were using to project into the dispersion function and rotate it by exactly half the angle. Isn't that cool? So when you rotate that, you're going to translate the cosine. Let's look at this in a bigger picture. Okay? The cosine used to stop right at the edge, right? It doesn't now. It drops a little bit. So there's a second order Zeeman shift here. And there's even a little bit of a shift down here, singlet shift, because the thing moved off the bottom, right? Bottom moved over. So you got a little bit of a second order shift right there, okay? And then you just below the other ones, what the hell, right? These two used to be on the same line, right? And so for these two as well, you see? So we split our old spectrum here, this hexagonal projection, got split first order. First order. And you can see that just from the geometry. Isn't that cool? So you're definitely going to split your doublets. But you see, this doesn't stop. I just keep cranking the gauge up. I'm just moving this thing along. It's just a cosine that goes forever. I can move it all the way through 2 pi and come right back again. I can put these levels anywhere I want if I use enough gauge parameters. Just this one alone, the first, this is nearest neighbor only. But I can start putting them on the other ones. I can put the levels anywhere I want. I've got 6 parameters total then. Right now it's 2 plus 1, 3. Got 2 more to go. Okay, now the rest of this I'm going to go through very quickly. I just want to point out that I can make any dispersion function I want, even a gauge dispersion, but certainly with real parameters I can make the ordinary kinds of dispersions. I can even go up and do something we're going to do later, which is octahedral symmetry. I can make a 6th thing into an octahedron. That's an octahedron there. I don't know, have my octahedron? Yeah. Here's my octahedron, right? You can either look at it on the 4-fold side, or you can look at it on the 3-fold side, right? See the shadow? Try to keep my hands out of there. It's hard to do. I could just hold it like that. You see the shadow? Hexagon, right? Okay?
That's right.
You've got to get it at the 1, 1, 1 direction, right? There's an octahedron, okay? Later we're going to talk about tunneling of angular momentum around in a molecule like this, and we're going to see spectra that looks like that. And that's exactly what you get with this matrix when you set it up with those parameters. Take some, off neighbor parameters to do this. Okay, that's for later. Okay, now I want to show some dynamics of waves. These are continuous waves with n equals 72 or 172, or over on the wall we've got 144. There's the character table over there for 144. I don't know if you want to even try to pick that up on the cameras. It kind of looks like four of our 72s, because the 72 has been doubled and therefore squared to 4, and that makes 144. Cyclic group, and you can see the structure of it. So after a while, it gets to be a continuum. So we're going to play with continuous waves here, just to get a feeling for what the dispersion function can do for you. And we're going to use the dynamics of 2 things excited at once, not just an eigenstate, but an eigenstate plus some other eigenstate. So we're going to have a thing that we want to factor, because we want to split this into an overall phase and then something inside, the guts of the wave, if you will. Or I should say, it's probably better to call this the guts and that the skin, because that's what you're going to see. If you take an absolute square of this factored wave, this is going to go to 1. And you're just going to be left with this. And so eventually, that's the thing you measure, and the square of that is a body count of, if it's a quantum mechanical particle finder, you're just going to have a pile of particles here, nothing right there, and then again and again, all around the ring, or whatever this space is. Okay? So, envelope or modulus, the wave skin, plus or minus the cosine of A minus B. Half difference. And the inside, real part and imaginary part, this is the wave still alive. Its heart is still beating, okay, filling the skin, okay, with a real part and an imaginary part, you see. That's the phase part. And so that's what I call the anatomy of a 2-state wave function, okay. So your classical stuff is going to be coming out of a psi star psi. But what made that wave live? These two parts are needed. The phasor is going everywhere. Okay? So we're going to do a fundamental analysis taking this expo cosine identity that lets us factor a wave. And I'm going to just use the simplest case, a 50-50 sum here. You don't have to make it that way. You can get other combinations. But let's do the easy thing. So I'll have a K1 and a K2 that has an omega 1 and an omega 2. And what I'm going to do is I'm going to put this together as a sum and then factor it. And what I'm going to be seeing, of course, is right here, I'm going to be seeing a half sum of the k vectors and the half sum of the frequency vectors. That's for this part. And then for this part right here, I'm going to be seeing a cosine of an argument that has the half difference and of the k vectors and the half difference of the frequencies. So that is what we're working at. So we're looking at the overall or mean phase here, where omega p is half sum of the two frequencies and kp is half sum of the k vectors. Then these are the differences of frequency and k vector, which we call the group phase. Meaning no connection between group and group theory, at least not directly. Group means a lump, an envelope. Okay? All right. Well, given that, we can figure out, first of all, the phase velocity of one of the components is simply the ratio of omega over k. That checks with units. This is per second. This is per meter. So this is per second per meter. That's the same as meters per second. Okay? And we've got two of those going in. Okay? So there's a velocity for this and a velocity for that are going to mix and interfere according to this rule and give me a phase velocity and a group velocity. The phase velocity being the ratio of the two factors here. Now, let's make sure we know what we're doing here. When I say this is the velocity, what I mean is I'm going to say how fast does this phase, a particular value of it, go. Let's say how fast does k1x minus omega 1t equals 0 go? Well, that's given by x equals omega 1t divided by k1, right? Namely this is the coefficient of time. Well, I do the same thing with each of these right here. I take the ratio of this to this. That gives me this velocity, which we call the phase velocity. And this is the group velocity, which is that. Okay? Now we're going to represent these things in per space-time by vectors. Okay? If this is a vector omega 1 and k1, this is a vector omega 2. Very nice geometry. I'm going to give you a very non-typical dispersion function. Okay? But there are bands, lots of solid-state bands that look like that, so it's not that out of line. Not for the ground state, probably. But anyway, I'm going to pick a k1 that slopes, right, has a slope equal to a velocity, okay, omega over k, all right? And that'll be number 1. There's number 2, okay, typical value. I pick this state and this state, okay, and those are their omegas and k's. Now, we're going to make something out of that. Well, this is what you're going to see. You're going to see, first of all, inside the thing, the phase. Half sum, there's the whole sum, there's the half sum. Okay, so there's k phase right there. Okay, and then I need the difference, half difference. Okay, I need to take this thing minus, add it to k1. Okay, and then that'd be down here. I want half of that, okay? It would be right here, and that's half of it right there, okay? So those are the two vectors that define what's going on. This one's going to have the guts going along at some speed. This thing's going to have the outside of the thing going backwards. This is part of what's called a backward phase amplifier. Now, we're going to study this one, linear dispersion. Suppose I have a K1 here and a K2 there. That's the easiest problem in sophomore physics. Okay, same frequency but opposite direction. Okay? So here's the half sum. There's the half difference. We got to look at some pictures of things like that. But before we do that, let's just go through what kind of dispersion relations there are. This is what I call the movie marquee or Christmas light dispersion function, constant. This means that you've got a bunch of oscillators lined up that all have the same frequency, but some of them have different K values. Okay? So, pick one of them, right? What's it going to look like, right? Well, it's going to have a K value, it's going to have a frequency, so that means it's going to move at omega over K. That's the way you get a marquee pattern to move. No matter what structure I put there, everything I do with this is just going to move. They're not coupled.
Do they have the same velocity? No?
No, they don't. So you can make them go fast or slow.
Oh.
And when you make K equals 0, they go infinitely fast, right? You go blink, blink, all of them, right? That's an infinitely fast. That's an instanton, infinite velocity. Omega over K, K is 0, infinite, right? Then as I tip myself over like this, I start to get something that's less than infinite. So uncoupled pendulums. That's what it is. You can set any sort of distribution you want, and these pieces will all go to different speeds. And it's kind of fun just to play with this system. This is sort of the opposite. Linear dispersion. This is what light does in a vacuum. Exactly. And sound, approximately. Phonons, approximately. Weakly coupled pendulums, no gravity. Okay? Straight line. Then, weakly coupled pendulums with gravity, or light in the fiber, approximately, or non-relativistic Schrodinger matter equation. Parabola. Okay? Badly drawn parabola, but that's what I meant by gravity. Then remember, the thing that we're getting with the phonons, right? That's a very famous one. Okay? Strongly coupled pendulums, no gravity, or acoustical mode in solids. This is just a general exciton. Strongly coupled pendulums with gravity, optical mode in solids, relativistic matter. If this is a hyperbola, we're going to get that today before we finish here. So that's the one I picked. I picked a sort of a sneaky one there, which is shown on the next slide here, blown up. Okay. Now the idea is to analyze what's going to happen if I pick two of these states, for example. Okay. If I pick these two, then I've got a vector here and I've got a vector there. I'm going to take the sum, which would be here, but I'm going to take half the sum. So that's going to be my phase, my mean velocity for an 8-3 combination. And its slope, you see, will be determining something. Now, here is the group. Okay, the group vector is pointing this way. Okay? So omega 8 minus 3 over K 8 minus 3, that's the slope for group velocity. Okay? So phase velocity and group velocity, two things you're going to see when this thing runs. Okay? What else do I have here? I have another example over here where I picked these two. See, there's the mean phase velocity slope, there's the group velocity. So you get all kinds of crazy motion with dispersion functions that are snaky like that. And this is the way to analyze it, to see what will happen. Okay, now what I want to do is I want to go ahead and I assume I have some phase and some group values. In other words, I'm going to just pick a K1 and a K2 and then do the half sum and half difference, or else I'm going to pick the phase and the group, and I'm going to do this is my source. My source will be a K1, which is the sum of the phase and the group, and my other source will be a difference of the phase and the group. Okay, so this is just, let's pretend. Let's pretend that these are my phase and group vectors. There's a dispersion function coming along about like there, okay? But these are just 2 points on it. The dispersion function might go all crazy in between and come back here. That doesn't matter because we're only exciting these two. So far, so good. What do we get in space-time? That's the question. Okay? What do those do? Right? Well, just remember what they are. Omega P, omega Kp, omega G, Kg. Okay? Mean phase, relative group phase. Okay? And we are going to balance them 50-50. If you don't balance them 50-50, you get some extra motion, which we'll talk about much later. Okay? So we're going to be looking for the zeros of the real part of this to analyze it. So I already got a real thing here, so I don't have to do anything. But with this one, I'm going to take cosine of the phase variables, just like I did there. Okay? So that's what we're going to plot on the computer. But we've got to figure out what it's going to do. It's going to make a coordinate system in space and time. A screwy, what they call affine coordinate system. That means not fine. It means that instead of being nice Cartesian, it's crunched. That's what we're going to get. Now, why are we going to get this? Because if I'm asking for zeros of cosines, I'm taking multiples of pi over 2. Odd multiples, actually. I'm a little bit mistaken by putting even numbers there because that's not quite what I'm after. But let's just solve it anyway. Okay? What I'm going to get here is that the phase part of this wave had better be a multiple of pi over 2. And if I'm talking about lattice points where they intersect, I want this one also to be 0 at that point. Remember, what you're getting by writing these is a factoring of the wave. So if the group is sitting here and a phase is sitting here multiplying each other, and this one goes to 0, this can't do anything about that. It will be 0 because of this one. This can be anything less than infinity, and this is going to kill that moment. And then again, if this one is 0, this thing can't do anything about it. So that's why I'm drawing lines here like this. But we're interested in where they're both 0. That's where these lines are going to intersect. So this is the equation we have to solve. This will tell us what the lattice vectors are in there. Okay? So I make it into a nice little matrix equation. Okay? NP and NG times pi over 2 is equal to kpx minus omega pt, and then the group equation is k group times x minus omega g times time. So far so good? Okay, let's invert it. You got to take a determinant of this matrix. That turns out to be the determinant of the cross product of the kg and the kp vectors. Take the cross product of that. Better not be 0 or I'm done. Right? I cannot stand to have these things in the same line and get a coordinate system. I can't, that won't work. But if this is non-zero, this will give us something. And look what it gives us. It gives us whatever this integer is times omega g kg. But be careful, because this is a coordinate system, you see, that has the kg omega g. This is flipped. And then another integer times this one right here, omega p kp. So basically it's these vectors reflected around the 45-degree line. That's what the unit vectors are going to be. And that's what they look like. If the vectors look like this, the lattice is going to look like that. I got to flip this guy around the 45 to give this one. That'll give me these lines. As soon as I find this one, which is flipped down to here. Okay? It's down here. This one's up there. Okay? So those are the unit vectors. That's your lattice. These are the thing. Now, if you want to count the evens, you can. You get twice as many. But counting the odds is where you're really sure you're going to get a 0. Right? Otherwise, you're going to get a crest. So this is really giving you equations for the crests and the zeros. Okay? Crests, troughs, and zeros. Twice as much as you really want. Okay? Now, what's interesting is the sum of these two vectors. Half sum and half difference gave us them, but they themselves give you the original k's. And if you can make pulses that don't misbehave, these are the paths the pulses are going to travel. And you're going to something like that, maybe. But probably not. And we'll talk about that more next time. But let's just go ahead and do one here. Back to the old thing that gives us this. I want to take a really simple case. I want two lasers colliding. And the cross of these two is not 0. Here's the group. There's the phase. Okay? P for phase, or P for pitcher's mound. This is a baseball diamond. There's the pitcher's mound. Okay? There's the grandstand for group. Okay? GP. Mnemonics for Americans. Okay? So, anyway, what we're doing is we're saying, okay, I'm going to take a K1, which is just 1, 1, 45 degrees. This is going to be omega, and this is going to be CK. So this is light. That's the speed of light. This is minus the speed of light, okay, for the other one. Okay, this one. So those are your two vectors. Here's your half sum. Okay, it's 0, 1. 0 this way, 1 this way, that's the P. Okay? And then the half difference, omega A minus this. Okay? That gives me 1, 0. That's this thing. Okay? I used to call it dugoutness. Across the hall here, Woody said, hey, if you want a G, use grandstand. So these things take a while to settle, right? Okay. All right. So that's what we're talking about, and what we're talking about is two laser waves coming together to make a coordinate system. Okay. So let's really quickly here look at an animation of that, which is available on this program right here, Borit, which is on the web. This is an old version of it, but let's just look at what it does. There's the standing wave that results from a wave with two units. And I'll go ahead real quickly here and just zero this thing and put the 2 plus in there so that you can see what the wave looks like. This is kind of neat. There's the real part of the wave making little white zeros. The real part of the wave, and the imaginary part is 1/4 ahead, just like it should be in business. There's the actual phasor down there, which makes a cycloidic curve if you squint your eyes. Okay? But in any case, that's what's running this way, and then we run another one the other way. And I'm not going to try to balance them. I'll go back where they are balanced. and that's the result. So this is 1 micron at 600 terahertz. It's a beautiful green light that makes a grid, a coordinate system that's absolutely Cartesian in space and time. This is 1 micron here. This is about a femtosecond there. Okay? So that's what we're looking at right now, is this. The real part is making those zeros. Every once in a while, the real part goes infinitely fast. Bang, it's everywhere. And then it's gone. Bang. Every half period. Bang. You get the crossbars. Those are the x-axes. The time axis isn't going anywhere. So that's what we're really seeing. The group factor is not going anywhere. It's got zero slope. The phase part, and this is in per space-time, is infinitely fast. So far, so good? Okay? So that's the situation that we have on the blackboard here to start with. Just to swivel around, this is an incredibly complicated looking construction, but I want to get you used to it because this is the ultimate group theory of space and time here. Here's the right moving laser. Here's the left moving laser. Here's the baseball diamond. Here's the half sum, the pitcher's mound or the phase. Here's the half difference down here, the group or grandstand. So that's the baseball diamond before we get funny. Now what we're going to do is we're going to go fast enough through this light to Doppler shift this side by a factor of 2. And while we're doing that, we're going to be running away from the light that's coming from over there going left. So we have to have that. Now that's a result of time reversal symmetry. We'll talk about that later on. But let's go ahead here and just see what that looks like. First of all, I want to point out the actual numbers here. As I said, 1 micron here. These are half micron green wave, 600 terahertz CW, continuous wave laser. This is a continuous wave coordinate system. And we're talking about a 1 micron, 1 femtosecond is 10 to the minus 15 seconds. 1 micron is 10 to the minus 6 meters, a millionth. Okay? That right there, the period, is 5/3, because the speed of light is 3 times 10 to the 8th, approximately. This is what pulses, I want to show you pulse waves, look what they look like. They make baseball diamonds in space and time. Let's take a quick look at a pulse wave that has the same fundamental frequency. And you can see the phasors that I've turned on here include 2 and minus 2 are right there at the right. But then it has 4 and minus 4, 6 and minus 6, 8 and minus 8 in decreasing amounts so that I don't get a sine x over x wiggly thing. I get a nice smooth set of many baseball diamonds. They're all going C. Okay? Now let's come back to the main screen here and ask what I would get if I did a Bohr dispersion. Now this is something I'm going to do very quickly, but I want to just quickly show you that it's quite crazy. I'm going to have a K2 here and a K4 there. I call them the mystery sources. Okay, I'm going to have a K here that's 1, 2, that's frequency 1, K2, frequency, now I'm turning the frequency this way so that I can match it with space-time without having to do that flipperoo that we did. And then there's 1, 2, that's K number 2, and then K number 4 is 4 and 4. Okay? This happens to be a Bohr-Schrödinger matter wave, but I could just pick random values for these things and play the game I'm about to play here. Okay? First there's the phase. Half sum, there's the sum, there's the half of it. Okay? So far? There's the group, half difference, there's the difference, there's half of it. So those two vectors, the blue and the green, make a coordinate system that we're going to see. Here's the blue, okay, making its paths, okay, And then here is the green making its paths. Okay? Those are zeros. Okay? That's what you're going to see. And I'm going to try to reproduce that over here on the screen. Go ahead and keep it on this main screen for a minute while I fuss around here.
Sure.
And try to get this to work reasonably well. I think I've got it pretty close right there. Actually, that doesn't look so good, but I've made the mass too big is what I've done. But there's the basic idea. And what you can see when this is happening is the group is going at a different speed than the phase. The phase is the stuff inside. Okay? Phase is the stuff inside here. The phase is actually slower than the group. That's what's wrong with Schrodinger. Schrodinger's wrong with a situation like that. That is something we'll mention in a little bit. But I'm running it very slowly now. You can see the phase is making those zeros, but the group is making the others, you see. So they're very close in angle, just like this one, but this one is a little close. It's got twice the mass of that one. Okay? So you see the group guys are here with a very gentle slope. They're not, I'm sorry, the group is here with a steep slope. You know, look at it this way, a very steep slope, and the phase is here running along at a more leisurely, but still very fast. Okay? So that's, you know, no one cares about the phase well enough to correct this. And that's what relativity is all about, as we're going to see, is taking that into account. Now, if I want to make pulses out of this thing, I add the two vectors that I have and get my original paths back again. They're the original paths. Those would make pulses if the pulses could be held together. With this dispersion, they can't. So they make all the revivals and all kinds of crazy stuff that we'll talk about next time. But for light, I can do it. Okay, this is the whole thing with all of the arithmetic that goes with this particular example. But let's go back to linear dispersion. If I put two lasers in the same direction, then the cross product of the two vectors gives me zero area. So I can't make anything but a streak, a bunch of streaks. Because the group and the phase are going at the same slope, same speed. However, what we were just doing was crashing them into each other. Here's pulses crashing into each other. Here's what we were looking at when we made the baseball diamond with light, 600 terahertz light. Now, what's going to happen when I Doppler shift this to factor of 2 and have this? And now let's switch over to